You think you're touching something right now? Your fingers on a phone, your feet on the floor, your body in a chair. You feel it, the pressure, the texture, the weight. That's touching, right? That's contact. Two things meeting. Your skin and another surface coming together. Obvious, simple, real. But what if I told you that's not what's happening? What if I told you that in your entire life, you have never touched anything? Not once, not ever. Not your mother when she held you as a baby. Not the love of your life when you kissed them. Not the ground beneath your feet right now. You have never made contact with anything. Nothing has ever truly touched you. And you have never truly touched it. Sounds insane. Sounds like philosophy. Sounds like someone playing word games. But this isn't philosophy. This is physics. This is what's actually happening at the atomic level every single time you think you retouching something. And when you understand it, when you really see what's going on, it changes how you think about yourself, about matter, about reality itself. Richard Feynman understood this better than almost anyone. He spent his life looking at the universe, not as we wish it to be, but as it actually is. And what he found was stranger than fiction, more beautiful than any story, and far more disturbing than most people are ready to accept. Let me show you what's really happening when you touch something. Start with your hand. Look at it. That hand seems solid. It seems continuous. A thing. A single unified object. But it's not. Zoom in. Your hand is made of cells. Billions of them. Zoom in further. Those cells are made of molecules. Proteins, lipids, water. Zoom in even more. Those molecules are made of atoms. Carbon, hydrogen, oxygen, nitrogen. And here's where it starts to get strange. What is an atom? You probably learned in school that an atom is like a tiny solar system. A nucleus in the center with electrons orbiting around it like planets around the sun. Nice picture. Easy to visualize. Completely wrong. That model, the Bohr model, is useful for some calculations, but it's not what atoms actually look like. It's not how they actually behave. Electrons don't orbit like planets. They don't travel in neat circular paths. They exist in something called probability clouds. They're smeared out. They're everywhere and nowhere at the same time. They don't have a definite position until you measure them. This isn't a limitation of our instruments. This isn't us not being able to see clearly. This is the fundamental nature of reality at the quantum level. Electrons are not tiny balls spinning around a nucleus. They are probability distributions, fuzzy clouds of likelihood. And these clouds, these electron clouds, they define the outer edge of every atom in existence, including every atom in your hand, including every atom in whatever you think you're touching right now. Now here's the question. When you touch something, what exactly is making contact? Your atoms and the atoms of the other object. Specifically, the outer edges of your atoms and the outer edges of those other atoms. And what are those outer edges? Electron clouds, probability distributions, fuzzy quantum hazes. So when you press your hand against a table, what's actually happening is your electron clouds are getting close to the table's electron clouds, getting very close. But here's the thing. They never actually meet. They can't. There's a force that stops them, and that force is electromagnetism. Electrons are negatively charged. All electrons. Yours. The table's. Everything's. And negative charges repel each other. Push against each other. This is basic physics. Like charges repel. When you bring two negative charges close together, they push apart. So when you bring your electron clouds close to the table's electron clouds, they push back. They resist. They say no. And that resistance, that electromagnetic repulsion, that's what you feel as touch. You're not feeling contact. You're feeling force. You're feeling the electromagnetic force pushing back against you. The sensation of touching something is the sensation of being repelled by it. You are floating. Right now. Your hand hovering above whatever surface you think it's resting on, separated by an incredibly tiny gap. A gap so small, it's measured in angstroms. 1 angstrom is 1/10,000,000th of a meter. That's the scale of the gap between you and everything you touch. Tiny. Almost nothing, but not nothing. There is always a gap. There is always separation. There is always empty space between you and everything else in the universe. Feynman explained this with characteristic clarity. The atoms that make up those surfaces are held apart by electromagnetic forces. The closer they get, the stronger the repulsion. It's like trying to push 2 magnets together with the same poles facing each other. You can get them close, very close. That force pushing back, keeping everything apart. For all practical purposes, I'm touching things. And in everyday life, that's true. You don't need to know about electron clouds to use a hammer. The gap is functionally irrelevant for most purposes. But here's why it matters. Here's why Feynman cared about it. Here's why you should care about it too. Because when you understand this, you start to see that the solid world around you, a very convincing illusion, an evolutionarily useful illusion, but an illusion nonetheless. Think about what an atom actually is. A nucleus containing protons and neutrons surrounded by electron clouds. The nucleus is tiny. If an atom were the size of a football stadium, the nucleus would be a fly in the center of the field. Everything else is empty space. Electron probability clouds filling that space. But those clouds are not solid. They're not stuff. So atoms are mostly empty. And you are made of atoms, which means you are mostly empty. The chair you're sitting on is mostly empty. The floor beneath you is mostly empty. Everything solid is actually almost entirely nothing. So why does anything feel solid? Why do you fall when you jump instead of passing through the floor? Because of forces. The same forces that keep your electron clouds separated from the table's electron clouds also keep your entire body separated from the floor. They keep the molecules of your skin bonded together. They keep the atoms of the wall locked in place. Solidity is not about stuff. It's about electromagnetic interactions between electron clouds. He loved revealing the strangeness hiding beneath ordinary experience. He once said that if you really want to understand nature, you have to be willing to let go of your intuitions. Your intuitions evolved to help you survive on the African savanna. They evolved to help you find food, avoid predators, attract mates. They did not evolve to help you understand quantum mechanics. So when quantum mechanics tells you something that contradicts your intuition is wrong. Not partially wrong, not approximately wrong. And the idea that you touch things is one of those intuitions that quantum mechanics completely destroys. Let me go deeper. There's another principle at play here, something even more fundamental than electromagnetic repulsion. It's called the Pauli exclusion principle. Wolfgang Pauli, physicist, Nobel Prize winner, figured this out in 1925, and it's one of the strangest rules in all of physics. The Pauli exclusion principle stated that no 2 fermions can occupy the same quantum state at the same time. Fermions are a class of particles that includes electrons, protons, and neutrons, the particles that make up ordinary matter. What this means is that electrons in an atom cannot all pile into the same energy level. They have to spread out. Each electron has to have its own unique quantum state. And when 2 atoms get close together, the electrons in one atom cannot occupy the same states as the electrons in the other atom. They're excluded, forbidden, not allowed. This creates a kind of pressure, degeneracy pressure. Even if you remove all the electromagnetic repulsion, even if you neutralize the charges somehow, the Pauli exclusion principle would still keep atoms apart. Electrons would still refuse to occupy the same states. They would still push back against compression. This is why matter is stable. This is why you exist as a distinct object separate from your environment. The Pauli exclusion principle is holding you together and keeping you apart from everything else at the same time. So when you touch something, you're not just experiencing electromagnetic repulsion. You're re-experiencing a quantum mechanical rule that says the particles making up your hand and the particles making up the table cannot coexist in the same space. They are fundamentally, ontologically, excluded from each other. Touching is not contact. Touching is exclusion. Touching is the universe enforcing its deepest rules about what matter is allowed to do. Now let's think about what this means for your experience of the world. Every sensation you have of touching something, the warmth of a coffee cup, the smoothness of glass, the roughness of sandpaper, all of them are your nervous system interpreting electromagnetic and quantum mechanical forces as texture, as pressure, as temperature. Your brain is receiving signals from nerve endings in your skin. Those nerve endings are detecting forces. The forces are caused by electron cloud interactions. And your brain translates those signals into the rich qualitative experience of touch. But the experience is not the reality. The experience is a representation, a model, a useful fiction your brain constructs to help you navigate the world. The reality is forces. The reality is electromagnetic repulsion and Pauli exclusion. The reality is electron clouds hovering near each other, but never meeting, never merging, never actually touching. Feynman had a way of putting this that stuck with people. He said, imagine you're pressing your hand against a table. You feel the table. It feels solid. But what's really happening is trillions and trillions of electrons in your hand are approaching trillions and trillions of electrons in the table. And every single one of those electrons is pushing against every single one of those other electrons, repelling, resisting. The force adds up. Of touch, but at no point does any particle in your hand occupy the same space as any particle in the table. At no point is there actual contact. The gap is always there, infinitesimally small, but infinitely real. Here's where this gets even more interesting. What about all the physical phenomena that seem to require contact? Friction, it turns out, is also electromagnetic. When two surfaces slide against each other, the electron clouds of the atoms in those surfaces interact. They attract and repel in complex patterns. They form temporary bonds that immediately break. The energy required to break those bonds and the energy released when they form, that's friction. It's all happening in that tiny gap between surfaces. No contact required. Heat transfer works similarly. Those vibrating atoms cause their electron clouds to fluctuate. Those fluctuations interact with the electron clouds in your skin. Energy transfers. Not through contact, through electromagnetic interaction, through forces reaching across that microscopic gap. This is what Feynman meant when he said that if you really look at what's happening, if you really pay attention to the physics, the everyday world dissolves into something much stranger, much more abstract, much more mathematical, but not less real. If anything, more real. Because you're no longer fooling yourself with comfortable intuitions. You're seeing the machinery underneath, the actual mechanism, the way nature really works. Now let me take this even further. What happens when atoms do get extremely close? Closer than normal? What if you could somehow force them together past the point where electromagnetic repulsion usually stops them? This is what happens inside stars. Inside the sun, temperatures and pressures are so extreme that atoms are forced together despite the electromagnetic repulsion. The result is nuclear fusion. Hydrogen nuclei merge to form helium. Mass is converted to energy. The sun shines. And even there, even in the most extreme conditions we know of in the natural universe, atoms don't truly touch. They overcome the electromagnetic repulsion by having enough kinetic energy to get close enough for the strong nuclear force to take over. The strong force only operates at extremely short ranges, shorter than an atom. It's what holds protons and neutrons together in the nucleus. But even the strong force doesn't make things touch in the way you intuitively think of touching. It's just another force, another interaction, another way for particles to influence each other without ever truly making contact. What about at even more extreme scales? What about inside a black hole? Nobody knows for sure. The physics breaks down. General relativity predicts singularities. Quantum mechanics predicts something else. We don't have a complete theory that covers both. The concept of touching, of contact, of two things being in the same place at the same time, it doesn't apply the way your intuition suggests. At the quantum level, particles are not little balls. They're excitations in fields. They're probability distributions. They don't have hard edges that can touch other hard edges. Feynman was always trying to get people to see this. He was frustrated by the way physics was taught. He thought too many people memorized formulas without understanding what they meant. Even the logic changes. Quantum mechanics is not just classical mechanics with smaller pieces. It's a fundamentally different framework. And if you try to understand it using everyday intuitions, you'll get confused. You'll get frustrated. You'll get wrong answers. The fact that you never touch anything is one of those truths that reveals the gap between everyday experience and underlying reality. It's not a trick. We have scanning, tunneling microscopes that can image individual atoms. We have particle accelerators that can probe the structure of protons and neutrons. We have quantum computers that exploit the weird properties of quantum mechanics for computation. All of this technology, all of this knowledge, all of this understanding is built on the recognition that atoms are mostly empty and that what we call touch is really electromagnetic repulsion. So what does this mean for you? You can go on touching things the way you always have. The physics doesn't change your experience. Because once you see this, once you really understand it, you start to notice how much of what you take for granted is a construction, a model, a representation that your brain creates to help you survive. Feynman thought this was the whole point of science. Not to confirm what you already believe, not to make you comfortable, but to show you what's really there, even when it's strange, even when it's counterintuitive, even when it's hard to accept. Just naturally. It helps you manipulate objects. It just doesn't happen to be true. There's something beautiful about this, though. Something profound. If you never touch anything, if you're always separated from everything else by these microscopic gaps, then what is connection? What is intimacy? What is love? Because connection isn't about contact. It's about interaction. It's about influence. The way forces pass between you across those infinitesimal gaps. You are connected to everything you touch, not through contact, but through force, through energy. That's more intimate than touch. He didn't believe in pretending the universe was simpler or friendlier than it is. Willing to let go of easy answers and sit with the strangeness until it became familiar. It's unsettling. It contradicts everything you thought you knew about your body and the world around you. But it's also fascinating. It opens up questions. It leads to deeper understanding. It connects you to the quantum realm that underlies all of existence. And here's the final piece. The thing that makes this more than just a fun fact. It's made of the same stuff as every other gap in the universe. The same electromagnetic fields. The same quantum mechanical rules. That keep the sun burning, swimming in a sea of interactions. Every moment of your existence, trillions of electromagnetic interactions are happening in your body. Forces reaching across gaps. Not a solid thing moving through space, but a pattern of forces. A dynamic equilibrium. The atoms that make you up will eventually disperse. They'll become part of other things, other people, other planets, other stars. But the forces that hold you together now, The electromagnetic interactions that give you form, those are eternal, unchanging until its end.